Okay, so let us start today's lecture. I think this will be the last lecture before your midterms. Okay, so we will be after this lecture, we'll be meeting for a lecture only after the midterm. So today we'll be talking about the pipeline data path and control. Before that, again, so just a brief review of what we discussed in the last class. So can you tell me what we discussed in the last class? What topics did we discuss? So we talked about mainly talked about branch prediction, and that too we were talking about two-bit prediction. So what are the two different types of prediction schemes? So one was uh, two-bit prediction scheme where we use something called a saturation counter. Okay, where depending upon whether your outcome is not taken or taken, you either decrement or increment, and you saturate it at 0, 0 or 1. And then we saw other type of two-bit saturation, two other type of two-bit dynamic prediction scheme, which is slightly different. So the difference between those, what was the main difference between those two prediction schemes, two-bit prediction schemes? What is the main difference? So if you say that there are some strong states and weak states, one rule was followed every time. And weak states were different in both. Okay, so again, weak states different meaning what? So in the earlier case, in saturation counter case, okay, whenever you had a transition, okay, so one weak state from one week not taken, you could directly transfer to weakly taken on. If you want to shift to taken state, you have to go to weak state and then go to strong state. Whereas in the second type of two-bit prediction scheme, you can, if your prediction is wrong twice, you directly jump to the strong state. Okay, so that's like the difference. So if you remember the state diagram that we had drawn, okay, so for two-bit saturation counter case, we if assuming that your initial prediction was strong not taken, and you initialized your state machine to 0, 0, then for every wrong prediction, for taken prediction, you go to 0, 1. If the so for taken outcome, you go to 0, 1. If the outcome is again taken, you go to 1, 0. If the outcome is again taken, then you go to 1, 1. In the second prediction scheme, you initialize your, assuming that you initialized your state machine to 0, 0. Okay, and then you're predicting that the outcome is not taken. If at all, if the prediction is not taken, if at all the outcome is taken, then from 0, 0 you go to 0, 1. In 0, 1, if the outcome is taken, where do you jump to? In the second scheme that we discussed, if you are in 0, 1 state and if your outcome is taken, to which state do you jump to 1, 1? Okay, that's the difference. To whether you will jump to 1, 0 or 1, 1. Okay, where 1, 0 represents weak state and one weak taken state, and 1, 1 represents strong taken state. Okay, so that is where the difference lies between the two schemes that we discussed. Okay, so we did some extensive. We discussed extensively about what is the importance of number of entries, whether you require unlimited entries. We saw some benchmark results also. So one thing that you have to understand from branch prediction scheme is you don't have to have a separate entry for each branch. You can have a limited number of entries. So in that case, multiple branches might change the same entry. Even in that case also, you are getting very good prediction results. So the misprediction was about 10%, meaning your prediction accuracy was about 80% in the worst case scenario, which is still very good. Okay, that's what we discussed in the last class. So today we'll start discussing about how do you modify the data path that we had drawn. Okay, initially we had drawn a data path for single cycle. Now we are trying to modify that data path so that it will be applicable for pipeline processor. Now, when you design a pipeline processor, then there are problems which are called hazards. Now, how do you detect those hazards? How do you actually implement forwarding? So all that we'll be discussing at block level in this particular topic. Okay. So let me just go through this particular topic. So initially, as I had mentioned, so we discussed about the single cycle data path. So this was our single cycle data path. I'm not showing control here. We'll discuss control separately. Okay. Now I just modifying this data path. Okay, so you observe the differences. Okay, so this was the earlier data path and just modifying it without changing its functionality. So this is our original data path and this is the modified data path. Okay, so for initial modification, this is still single cycle only. Can you tell me what modification did I do? So from the previous one, what modification did I do? So this was my earlier data path and this is my modified data path. This is still single cycle only. It's still not pipeline. The only thing I'm doing is the multiplexer, okay, the PC source, whatever I had used, okay, which was used for selecting PC plus X or PC plus 4, that multiplexer was there, no? That multiplexer, I am pushing it here. Okay, so that's the only change I'm making in this particular data path, okay, just for proper representation, okay. So that might not have a big impact on, not have any impact on the overall execution, okay. Now, the second thing that you have to do whenever you want to construct a pipeline data path is you have to first divide it into stages. Okay, so this is my instruction fetch. This is my instruction decode or a register file stage. And then you have the ALU or EX stage. And then you have the data memory stage. And then you have the write back stage. So these are the different stages of your processor. Okay. Now, and this is how the data typically flows in the except for one case where you are writing into the register file, the data goes back, but except for that, most of the cases, and again the PC change is also happening in this direction, but except for that, most of the data flows in this direction. Okay, except for that and except for this one. So whenever you want to implement, let's say the first instruction is required in the decode stage while the second instruction is fetched. So if you talk about this representation, we saw that in the second cycle, when the first instruction is getting decoded, okay, I have to fetch the second instruction, right? So in that case, how do I make sure, okay, how do I make sure that the first instruction code is not deleted? How do I make sure? So that is a fundamental concept of pipelining, right? It's not just dividing stages. After you divide the stages, what should I do so that the data corresponding to the first instruction is not lost? What do I make sure of it? You latch it, meaning what do you do? What do you mean by latching? What elements should I introduce? What elements should I introduce to latch it or to save it? So what do I introduce? So I will be introducing a register. Okay, so register is nothing but, okay, register is nothing but it's a series of flip-flops. Okay, so if you have, if you say there is a 4-bit register, it is nothing but there are 4 flip-flops which can store a 4-bit data. Okay, so that's the idea of a register, as you have already seen that as part of your digital design course. Okay, so how to retain the code for the first instruction while the second instruction is being fetched is basically you to use storage elements in between successive stages. So that is why I'll introduce the pipeline registers in between. Okay, so once I identify where to divide, I introduce the pipeline registers. So these are the different stages that I represented using different color codes. So this is my instruction fetch stage. So in between instruction fetch and this is my instruction decode stage, then execution, then memory, and then write back. Now I have introduced the pipeline registers. So these are, since I am using these registers for pipelining purpose, they are also called as pipeline registers. Okay, pipeline registers. So in MIPS or in RISC-V processor, so I'll be requiring 4 pipeline registers between the successive stages. The pipeline register are named as this. Okay, so IF/ID is one pipeline register which is there between the IF stage and the ID stage. Similarly, you have ID/EX register which is there between your ID and EX. Similarly, you have X/mem register and mem/write back register. So I'll be introducing 4 pipeline registers to make this a pipeline processor. Okay, but there is one major error in this data path. If I just introduce these pipeline registers and if I think that this will work as a pipeline processor, it will not. Okay, there will be one major problem that is there in this data path. Can you identify what is the problem? Can you identify what is the problem? So there is one major problem. It's not a small problem which you can rectify very easily, but one very big problem. We assume that we are working on only two instructions, overwriting of register before the data is used. Hazards, so we again hazards we'll discuss later, but even again, if not for hazards, even if there are no hazards also, this will not correctly work. No, even if you assume multiple instructions also, it should work properly, but this will not work. Okay, there is a very big error here. Race condition between pipeline registers. No, that will be taken care. No, that your registers or your data paths are designed such that you don't get any setup and hold violations. That you'll make sure with the help of design as well as by choosing the correct clock period. Okay, that you'll make sure of. Synchronization, no. Again, synchronization, I'll make sure that there is synchronization by choosing the clock period for in such a way that whichever stage is taking more time, that I'll choose as a clock period. So that also is not a problem. Transfer of code between registers will happen here in this data path. That is not an issue. There is one very fundamental problem. Okay, if you analyze this data path, then you'll understand. Again, synchronization issue can be solved by choosing a correct clock period. Since anyway the data will be transferring from one register to other register, if I just make sure that the clock cycle period is such that all the stages will be able to complete. Each stage you will be able to complete within the decided clock period. If you make sure of that, that will be not a problem. Anybody? Anybody still can guess a correct answer? You don't see any problem here? The PC generation also, it's not a problem here. That's not a big issue. And again, that's not an error. So PC generation will happen normally. So for normal instructions, you are actually going by this path. For only branch instructions where your branch condition is getting decided, you are taking this path. Or if you are implementing branch prediction, then you can move this whole thing inside the instruction fetch also. That is like implementation point. Something with the muxes, multiple input to a register. A register can have multiple inputs. That's not a problem. And remember, each register is not of the same size. Okay, that is one very important point I'm telling you right now. Each register is not of the same size. Okay, each register size is different. We are just talking about the data path. Can you take a guess how much? Again, I'm not including control signals. Control signals will require another set of registers, which I'll explain. Another set of storage elements. Okay. But if you're just talking about the data moment, can you take a guess what will be the size of this register? What will be the size of this register? What will be the size of this register? This is simple enough. So can you predict what will be the size of this register? 32 bits? Only 32 bits? See, you have to see actually what is happening. Okay. So through this register, you are sending not just the instruction code, you are also sending PC also. Okay, because that is required for your PC plus X calculation. Okay, your condition will be evaluated here, and based on that, you might have to choose PC plus X. So I'll be sending 64 bits here. And similarly, you'll be able to identify the size of this. So what will be the size of this register? Can you tell me? What will be the size of this register? The ID/EX. So you have one data here which is of 32 bits, the other data which is 32 bits. Then you will be using this sign extension block, which will sign extend to 32 bits. And then this PC is also sent for the next stage, which is again 32 bits. Total how many? So it's 32 into 4. Why do you get 5? Did I miss anything? Why do you get 5? So 32 cross 4 only. Instruction code you don't send. You don't send instruction code. Instruction code is not required. Once you pass it to the next stage, only the data that was read is required. Okay, anyway, that is a different topic. But again, anybody is still able to find some error here? Okay, I'll explain you about the error. So if you analyze the data path with respect to the time representation, so can you tell me in the 5th clock cycle, okay, which instruction should supply the right register number? Okay, in the 5th clock cycle, which instruction will actually write into the register? Is it the first instruction, second, third, or fourth? Which instruction should write into the register in the 5th clock cycle? The first instruction. If the first instruction is writing into the register, from where should you get the right register number? There is something called as a right register number, right? Which is basically a register code. Okay, right register number. Okay, which is basically your register code. Okay, whatever you can call it as right register number or code or whatever. So who should supply your right register number? First instruction, second, third, or fourth? First instruction only. Because the first instruction is supposed to write into the register, you are supposed to supply the right register number by the register right register code, which is specified as part of the first instruction. But is it happening here? Okay, is it happening here is what we'll see. Let's assume that again. So we have to basically identify what is getting here. Okay, what is being written here? Let's assume that, for argument's sake, you have this instruction available in instruction fetch stage, this instruction available in decode stage, this instruction available in EX stage, this instruction available in your memory stage, and this is the instruction that is available in the write back stage. Okay. Now, which instruction should specify? So here, tell me which is your first instruction. This is at the end of in the 5th clock cycle. You might see this as the status. Okay, but which is your first instruction here? This is basically your space representation that I will explain later a little more in detail, where you will be able to visualize how the actual pipelining moves. Again, there are two load instructions. There is load instruction here, load instruction here. So among those, which is the first instruction? The first instruction is this. The second instruction is this. Third is this, because the data has moved in different clock cycles. So fourth instruction is this. Okay, and fifth instruction is this. Now, in the write back stage, if this is the instruction that is there in the write back stage, now you are supposed to write into which register? You are supposed to write into which register? T1. That to everybody is clear. So I am supposed to write into T1 register. But who is supplying the right register number? Who is supplying the right register number? Which instruction is supplying the right register number? You check, where is this instruction coming? Okay, this instruction is coming from this register, IF/ID register. Okay, here I would like to clarify one more point. Okay, this is EX/mem and this is mem/write back registers, pipeline registers. Okay, so here I would like to clarify one more point. When I say that this instruction, okay, this instruction is available in the instruction decode stage. Okay, again, you might be a little bit confused, so that is why I'm clarifying this. When I say that this instruction is available in this stage, okay, this basically means that the data related to this instruction will be available in this pipeline register. Only then you will be reading, right? So this register will be supplying the inputs for reading of the registers, for reading of second register, and so on. Okay. So when I say that this is the instruction that will be available, even if you see in the earlier data path, if I show you, the problem is coming between the first and fourth instruction. Okay, because that is where there is an overlap between the writing and the reading. Okay, so here also the same thing is happening. When I say that a particular instruction is there in that stage, it is basically means that the data related to this instruction is available in this register. Then what about this instruction? When I say that sub instruction is available in the ID/EX stage, okay, in the EX stage, that basically means that the data related to this instruction or some information, okay, some information related to this instruction will be there in ID/EX pipeline register, and here some information related to this add instruction is available in EX/mem register, and some information related to this particular load instruction is available in mem/write back register. Then what about when I say that add instruction is there in IF stage? What exactly do you mean by that? So what is available here? What is available as part of the storage element? It's basically PC. Okay, the address of this instruction. When I say this is available in this instruction, the address is now available in PC. So maybe during the clock cycle, it would take this PC content, read the memory, and the instruction code for add instruction might be available at the output. It might not be loaded into the IF/ID register. It will be loaded into the IF/ID register when the next positive edge comes. But in the current clock, okay, so let's say if once the positive edge occurs, so if I'm talking about some time duration within this clock, okay, within this clock, if I am sampling, then this is the status. The address of that particular instruction will be there in the PC. Okay, again, depending on the time required, the data, the instruction code may be available, or it might be still in the reading process. That I don't know. Okay, that depends on the time taken for reading the memory. Okay, but remember this fact: whenever I say that some instruction is available in that stage, it basically means that the corresponding data will be available in the pipeline register, which is connected at the input of that particular stage. Okay, so that you should be very clear about. So the problem here is you are trying to write into T1 register, but here who is supplying the write register number then? If you assume our current analysis, if you go by our current analysis, who is supplying the write register number? Who is supplying the write register number? Now, write register number is given as what? So write register number is given as S1, but actually this is not correct. Okay, it should be T1. Okay, so the read register is correct. So your this instruction is instruction decode in which you have to read registers. So this part is correct. This being S0 is correct, but the write register number being S1 is wrong. So that's the major error in the data path. How do I correct this? How do I correct this? So there is clearly an error. So instead of T1 being the write register, S1 is being sent to the write register number, which is clearly wrong. So how do I modify this data path for the correct behavior? How do I modify this data path for correct behavior? Reroute the write signal from mem/writeback register, make write use a different register. Okay, so for that, I have to slightly modify the data path. What I'll do is, I'll not supply the write register number directly from here. Okay, what I'll do is, I'll reroute my write register number. Okay, that is your RD field. Okay, RD field, I'll not connect directly here. I'll reroute my RD field such that it also goes along with the instruction. Just like your instruction moves from one stage to another stage with the help of pipeline registers, your RD value for the corresponding instruction should also go through the different pipeline stages, and then finally it should be routed and connected back to the write register number. Okay, then only it will be coming. For example, initially you had, let's say, load S1 and something here, some S0 or something. So S1 is your write register number. You don't supply S1 here itself. So you pass S1 here. Once this goes to the next stage, S1 will move to the next stage. When this instruction will go to the next stage, S1 will come here. When this instruction moves to the, so when the instruction comes here, when instruction load S1, 0, S0 is in the write back stage, then S1 will be supplied as write register number. Okay, then it will be correct. So that's a very important modification that we have to do for the data path for the correct behavior. So write register number is not directly connected from the in the IF/ID stage itself. So the write register number has to go through the pipeline registers along with the instruction, and then you have to, in the write back stage, you'll be writing. So that is where you have to sample that write register number, and you have to reroute it back to the write register pin of your register file. Okay, so this is one very important one. Okay, so again, coming to the control signals, this also is very important. So control signals also should, just like you have write register, so control signals, just like you have the write register number, your control signals also should flow along with the instruction. Okay, it should not be that the control signals are generated and then used up there only. Okay, so for that, your controls control signals, how does they flow is, so you know that regs-write signal is required here, immediate select signal is required, and here ALU source here, ALU operation here. I'm just representing the different control signals required. Now you know that the control unit is here, which is generating all of the control signals. Now should I directly connect all control signals from this Should I correct all the control signals from here? Should I generate all control signals here only? Will that be correct? Will that be correct? If I do this, what will be the problem? So the control, all these control signals will be related to which instruction? So if I can directly connect the main control unit and generate all the control signals directly from the main control unit, so these control signals will be corresponding to which instruction? The instruction which is there in your ID IF/ID register, or the instruction which is there in this stage, the ID stage. Now, how do I make sure to avoid that? How do I avoid this problem? So how do I avoid this problem of wrong control information getting connected? Just like we avoided the read register problem, how the write register problem. How did we avoid the write register problem? How did we avoid the write register problem? So we move it along with the instruction. So here also we should do the same thing. Okay, so we carry it along with the instruction only. So what we have to do is we have to introduce. So since the immediate select stage is generated in the ID stage and it is required in the ID stage itself, you use that directly. What about regwrite? Should I connect directly from here or what? So regwrite is corresponding to which stage? Is it corresponding to read register stage? Does it correspond to EX stage? Or does it correspond to memory stage? Or does it correspond to write back stage? So what do you say? Should I connect this directly since it is there in the second stage? Yes or no? Should I connect it directly? No, because this is corresponding to write back stage. So the information which is there, the instruction which is there in the write back stage, that should be supplying the read register file. So this is not correct. So for other stages, how do I actually move is you send the control signals to the next pipeline stage and you use the control signals which are required in that particular stage. So if I pass the control signals, so this is like another register which is storing your control signals. So this is storing control signals for EX, MEM, and write back. It is not storing control signals that is required in the ID stage because you are generating your control signal in the ID stage itself. So there it will directly get used up. But the next stage control signals, you have to send it through the pipeline registers. Now, what should happen here? So once I move it to the next stage, your EX control signals will be used up here. Okay, so there are two signals which are required in the EX stage, that is your ALU source and your ALU operation, that ALU operation bits that we had decided. So those things will get used up here. Now, what should I send for the next stage? Should I send all this information or should I send only some signals? So which signal should I send it for the next stage? That is your memory stage. So you have to send only the control signals which are required for memory and write back. And here the signals which are required in the memory stage will get used up, which is your branch, your memwrite, and your memory. And then finally you send to the last stage only the write back signal, which will get used up. Okay, so which are the write back signals that will get used up in the write back stage? One is mem to reg. The other one is, which is the other signal which is used in the write back stage? That is your regwrite. So you have to reroute your regwrite signal from the data path. Just like you had done it for the register number, you pass it through different stages and you use the control signals in whichever stage they are required. All the other control signals have to move along with the instruction itself. Okay, so that's one more very important information with respect to the pipeline control. Okay, the other things remain the same. The generation of main control unit remains the same. Only thing is the control signals that are required in different stages also have to be moved along with the instruction. Okay, so that is what I'm trying to show here. Okay, so now let us see how exactly things happen in the hardware. So just I'll touch upon the concept of hazards. So specifically, we'll discuss about data hazards initially. Structural hazard anyway we'll not discuss because that is like we touched upon it and that's the extent of it. Okay, you have to make sure that resources are available. But with respect to data and control, we have to understand how exactly the data moves through the pipeline stages. So for that, we'll try to visualize. So for visualization, initially, I'll just touch upon the concept of hazards again. Okay. So if these are the instructions, so if these are the example instructions that you want to execute in a pipeline register, where S naught is basically the destination of first instruction, and S naught is being used as source in all of the remaining 4 instructions, meaning the last 4 instructions are dependent on the result of register S naught of the first instruction. If this is the case, can you tell me for which instructions do you face a hazard, and for which instructions you will not face a hazard? Which instructions you will face a hazard? I can go by the graphical representation. So if this is the graphical representation, assuming this entire thing happens in clock cycle 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so I assume that all of that is being done in different clock cycle stages. Okay, so in this case, can you tell me for which instructions you might face hazard and for which instructions you will not face any hazard? 2, 3, and 4. So when will your register be written? In which clock cycle will your S naught value be written into this register, into the S naught register? In which clock cycle will S naught value be written? In 5th clock cycle. Okay, in 5th clock cycle, the S naught value gets updated because your first instruction is entering the write back. Now, if it is entering into the write back stage here, which instruction will cause a problem? So for this instruction, where is S naught required? Where is S naught required? S naught is required at the input of ALU stage, so it might be required here. Similarly, for OR instruction, the S naught value might be required here at the input of the ALU stage, so that is why these will create a problem. Now, what about this instruction? Will it create a problem for this? Where is it required? Where will you be reading S naught from? Your S naught you will be reading from the register file. So you are writing into the register file and you are reading reading from the register file in the same clock. Is it allowed? Is writing into the register and reading from the same register allowed? That was our initial assumption. If you remember, I told you one assumption. So tell me, what is that assumption? What is the assumption with respect to the pipeline processor that we have been discussing? So when we started our discussion of about pipelining, I told you to assume few things. Okay. So with respect to the writing, we assume that in the first half of the clock cycle, the write will happen. In the second half of the clock cycle, the read will happen. Okay. But basically, in a single clock cycle, meaning in the 5th clock cycle only, the write can happen into S naught as well as read can happen to S naught, which is like this instruction. So if you see, then there will not be any problem with these 2 instructions because anyway the read and write can happen in the same clock cycle, and since by this time the write would have already happened in S naught, it will not cause any problem with this also. There will be no hazards for this and this instruction. There will be only a hazard for these 2 instructions. Okay. Now how do I solve this hazard? How do I resolve this hazard? So your S naught is getting updated here, but you need it here, and similarly you need it here. If I talk about clock cycles, in 5th clock cycle, your S naught value is getting updated, but your S naught value you require in 3rd clock cycle for this instruction, and in the 4th clock cycle for this instruction. So in this case, one way to avoid this is to stall. Okay, you have to stall this instruction and stall this instruction also. What is the other solution? The other solution is to basically forward. Now, how do I forward? The forwarding can happen. So now that S naught value is already ready here at the input of ALU stage, I can directly send it to, so this is in 3rd clock cycle. At the end of 3rd clock cycle, my S naught value is ready. And if the next instruction requires it, I can directly pass it to the next stage. So I can pass the data from 3rd clock cycle to the input of ALU. That basically means it is available at the input of ALU. Now, what about this? How do I solve the hazard with respect to this instruction? How do I solve the hazard with respect to this instruction? So for this instruction, where is the data required? Data is required here. So in this case, from which stage should I forward? So where should I forward? So here it seems a little bit tricky. So I have to forward the data from here. Okay, don't worry whether if you are not able to visualize. I'll show you a clear visualization with the help of the pipeline structure a little later. But here we'll be sending the data because that data has will be moving through the different pipeline stages. So by the time you require, by the time you come to the start of fifth clock cycle, the data will be available in this pipeline stage. Okay, so from there you will be forwarding to the input of ALU. So how is it done? That I'll tell you later. But now you understand that the first instruction, if there is a data hazard, the data hazard will be if you this is the first instruction, then the data hazard can be possible if there is if the second instruction is using the same source as the destination of first instruction, and also if the third instruction is using the same source as the destination of the first instruction. So in these two cases, you face hazard. Now, if this is the data dependency, then we call it as X hazard. Okay, this condition we call it as X hazard, and this condition where there is a data dependency between first instruction and third instruction, we call it as mem hazard. Okay, that depends on from where you are actually forwarding. You are forwarding from output of EX stage or from output of mem stage. So that is how this has been classified. So this is called as X hazard, and this is called as mem hazard. Okay, so more details I'll tell you as we go on. Okay. Now the next thing that you have to understand is how does forwarding actually work. Okay. So assume here also we are assuming one thing, that the forwarding can happen only to the input of EX stage. If you see here also the input is being, the data is being sent to the input of EX stage. Here also it is being sent to the input of EX stage. So this is one assumption that we are doing for our data file. Okay. So normally in the textbook, what they do, I'll tell you, they just explain this part. Okay, they just explain that this is what is called X hazard, and they'll give some conditions like this. Okay, so they'll give some conditions like this. Hazard condition is this for X hazard. Again, there are two possibilities. Your source could be the first source. The dependency can be with respect to first source, or the dependency can be with respect to the second source. So based on that, they just give two conditions. Okay, they just to give two conditions. So either X slash mem register read is equal to ID slash EX register 1, X slash mem register read is equal to ID slash EX RS2. So this is what they give for X hazard. Similarly, for mem hazard, they'll give these two as conditions. So if you just see these, okay, these conditions which, and if you just go through this explanation, it will be very difficult to understand. Okay, so you need to visualize how exactly the pipelining works. Okay, so I have made some attempt to explain the pipelining concept with the help of visualization. Okay, so now you, again, if you don't understand anything till this point in today's lecture, it is fine, but please pay attention in the next slides and see or try to visualize how exactly the data moves from one stage to other stage. Okay, then only you will understand how we came up with these conditions for detecting the hazard. Okay, so why did I choose ID slash EX? Why did I choose mem slash write back? And similarly, in the other hazard condition, why did I choose X slash mem? Okay, why not any other pipeline register? So all of that you'll be able to understand if you just focus on the next part of this particular lecture. So let's assume this is the pipeline structure. I have not shown the entire data path to make things a little bit simpler. Okay, I'm just explaining the important stages. So here you have instruction memory. I'm not showing the individual multiplexers and all. Okay, so that is just for simplification. Then you have the IF slash ID register here, ID slash EX, EX slash mem, and mem slash write back. Now let us assume some instructions. Okay, and this is the write register, which you know that it will has to go through the different stages, and the write register number will be routed from mem slash write back pipeline register to this point. Okay. Now let us assume that there are these instructions that are available. Now, one clock cycle time at a time, we'll try to analyze and see what is happening. Okay. Now, for that, we'll assume some initial data also. Okay. So, initial data, I'm assuming that the S0 contains 0, S1 contains 1 and S2 contains 2. Okay, meaning at the end of this instruction, what should be the S0 value? When I say add S0, S1, S2, at the end of this instruction, what should be the S0 value, which will be used in the next instruction? It will be 3. Okay, right? Okay, so that is our example. So at the end of first clock cycle, what I'll assume is, I'll assume that at the end of first clock cycle, the first instruction is already loaded into the if/id register, meaning it is available in this stage. Okay, it is available in the id stage. So here, important information that I'm showing is my source 1 is S1, my source 2 is S2, and my destination register is S0. Okay. Now, at the end of clock cycle 2, can you tell me what happens? So this is at the end of clock cycle 1. One clock cycle is completed. Okay, meaning this clock cycle, meaning even this hedge has occurred. Okay, this entire thing has already happened. That is my assumption. Okay, so at the end of clock cycle 1, this is the status. Now, what will happen at the end of clock cycle 2? Can you tell me? Can you think about? So this is your space representation. Till now, we have been seeing the pipeline concept with respect to time representation. Okay, but that is good if you are able to visualize. If you're not able to visualize, the space representation will help you to visualize how the data will exactly go through the stages. Okay, so now can you tell me what will happen in clock cycle 2? Okay, so in this stage only the registers might be read. So in clock cycle 2, what will be loaded in this register? id/ex, and what will be loaded in if/id register? What will be loaded in if/id register? So although I'm showing S1 and S2 and S0, basically if/id register will have the instruction code. And instruction code will have S1 field, S2 field, and S0 field. So that I'm specifying here. Okay. So at the end of clock cycle 2, what will happen is, so S1 register will be read, S2 register will be read, and what will be available here? What will be available here at the end of clock cycle 2? You would be reading S1 and S2. So what is the S1 value? 1. What will be the S2 value? 2. Okay, so that values will be available at the end of clock cycle 2. Okay, so let us show. So at the end of clock cycle 2, the first instruction has moved to id/ex stage. Now the values are read. Okay, S1 was 1 and S2 was 2. So those values are read. And your destination register has moved along with the instruction. At the same time, okay, because when you say pipelining, there is an overlap, right? So while the first instruction went and read these two registers, at the same time, your second instruction was fetched. Okay, your second instruction was fetched. So now if/id register will contain the instruction code for the second instruction. That means your RS1 field will be S0, your RS2 field will be S1, and your RD field will be S3. Okay, till this point, any doubts? So I've just showed how the data moves from one stage to another stage. Okay, now can you tell me what will happen at the end of third clock cycle? What will happen at the end of third clock cycle? Which registers will get filled? Which of the pipeline registers will get filled at the end of third clock cycle? And what will they get filled with? Any idea? So this is the current status. So at the end of third clock cycle, okay, so ex/mem will get some data. What data will it get? Now that the values are available at the input of ALU, they will be computed. And at the end of third clock cycle, the computed value, which is basically addition, you're doing the first instruction as addition. So there will be control lines which will be generated accordingly. And 3 will come here. So here you will have the destination register S0. And what happens here? id/ex, what will happen? In the id/ex, what will happen? Now RS1 is S0 and S1. So those values will be read. Okay. So at the end of third clock cycle, so your first instruction will now move to ex/mem stage, but now the data will be computed, meaning S1 plus S2 is computed, and S0 is basically the destination. So that has moved along with the instruction. And in the ID/EX stage, your second register information will be there, meaning you are reading S0 and you are reading S1. So S0 is still 0. It is not updated yet. Okay, S0 will still have 0. So it will be still reading 0, and S0, S1 is still 1, whereas the destination register is now S3. And at the same time, your third instruction gets fetched. Okay, this instruction gets fetched. So your RS1 field will now have S0, your RS2 field will now have S2, and your destination field will now have S4. Okay, so this is at the end of third clock cycle. So here you are clearly able to see the problem. What is the problem? What is the problem? So this is what we call it as hazard, right? What is the problem here? If you see at the end of third clock cycle, so where exactly is the hazard? So you know that S0 value at the end of this instruction, S0 value should be 3. But if you see, since it is pipeline processor, instructions will go on executing in a pipeline way. If you see here, S0 value is being read as 0. Is this correct? Is this correct? No. Okay, the reason is S0 should be updated by 3, but the updation will happen only in the write back stage. This instruction has not gone to the write back stage yet, and you are trying to compute the value for this instruction, meaning you are trying to add this instruction. You are trying to send 0 and 1 to the ALU, and you are trying to compute the value, which is not correct. So this will create a problem. So if I execute one more clock cycle, what happens is your 3 will go to the third stage, okay, for writing back. It's still not written back yet, but at the same time, you are already computed the S0 and S1, assuming the old value of S0, which is not correct. And you are trying to store 1 in S3. So this is a problem, okay? So this is what we call it as X hazard, okay? So this is a problem with respect to X hazard, where the second instruction is trying to read old value. The second instruction is trying to read old value, okay, and it is computing the wrong result. So this is your X hazard. Similarly, if I go for one more clock cycle, this is anyway wrong. Okay, so here, what is the expected value? What should be written into S3 register? According to the program, what is the correct expected value of S3? It should be 4. But here instead 1 is being written, which is 1 is being passed for writing, which is incorrect. Now, if I go for one more clock cycle, okay, the end of clock cycle 5, anyway, wrong result has already passed. Since the values were available here for this instruction also, this also would read the old value of S0, and you could have computed the value as a sum of S0 and S1, S2 as 2, whereas the correct expected value should be 5. Okay, for this instruction, you are doing S4, S0, 2, S2, right? So 2 plus correct value, which is 3, should be 5, but here you are trying to get a wrong value. So this is a case for mem hazard, where there is a dependency between the first instruction and the third instruction. Now, at the end of clock cycle 5, you have written the correct value. Your S0 has updated to correct value. Okay, but by that time, okay, by the time you come to the end of clock cycle 5, old value has already been read and wrong values are being written into the registers. Okay, wrong value will be written into S3 register and wrong value is being written to S4 register. Now, this is a condition of hazard. Now, how do you actually do the pipeline? Okay, so this is the problem. Okay, now let's go to finding the solution. Okay, so one thing is stalling, which we'll not discuss right now. Okay, so one solution to avoid the hazard is stalling. So when will you stall? So you stall. Maybe we'll discuss stalling later. So the second solution, what was the second solution for solving the hazards? The first solution was stalling. We'll discuss that later. But the second solution was forwarding. Okay, now I'll again reiterate the same steps. So at the end of clock cycle 1, you would have first instruction in IF/ID register. So this no problem. At the end of clock cycle 2, again there is no problem because I am reading the correct value of S1 and correct value of S2. Okay, so here also it's not a problem because your S0 is RS1 and S1 is RS2. Here also not a problem. But at the end of clock cycle 3, the problem starts. Okay, at the end of clock cycle 3, the problem is starting. Where is the problem? The problem is S0 has to be updated with 3, but that will happen only in write back stage. It has not gone to write back stage yet. Whereas you're trying to send to the ALU old value of S0. Okay, old value of S0 is being passed. So this is where the problem starts. Now, if I say I have to solve this problem with the help of forwarding, now can you tell me a simple solution? How do I solve this problem? How do I solve this problem? So I said I'll solve this problem with the help of forwarding. Now, how exactly should I forward the value? So I know that S0 value is 3, which is already computed here. And I know that S0 value is required at the input of ALU. What I'll do, I'll just draw a data path such that this value is taken, okay, such that this 3 is taken and it is sent to the input of ALU. Now, this is what you mean by forwarding. Technically, you are actually sending the data back. Okay, so data is sent back, but you still call this as forwarding. Okay, so there might be some confusion related to that, but try to understand you're trying to forward in the sense you are trying to forward the value for next clock cycle. Okay, you're trying to forward the value that is computed now as input in the next clock cycle. So that is why it is called as forward. Okay, but in Datapath, if you see the space visualization, you'll actually be sending the data from output of the ALU or from this register to the input of ALU. Okay, that is what actually forwarding means. So there might be some multiplexer here which will select this data. Instead of this data, which is old value, it will select this data. But when should I forward? Should I send this updated value every time to the input of ALU? I can't send, right? So there should be some condition. What is that condition? What is the condition? When should I forward this updated value to the input of ALU? When should I send? So when your destination of this instruction is same as source of this instruction. But if you see here, this instruction is there in ID/EX register. But here I don't have any RS1 and RS2 field, right? RS1 and RS2 fields are available only in IF/ID register. But here, if I want to know what is the source register for this instruction, there is no way of knowing it because I'm not storing it here. So what should I do in that case? Have to use a mux. Where will I use a mux? Again, please try to understand the problem. I know my destination for this instruction. Okay. To know whether to forward this value or not, I need to know here I have the data. I don't have the information about the register number. Okay. So here I need to check for the instruction that is stored in ID/EX register. I need to know what is the RS1 and RS2 field. Then only I'll be able to make the comparison and see if it is equal to source or not. Okay, but here I have no way of knowing it. So what should I do? So here I have to slightly modify the data path. Apart from storing since anyway these values are available as part of the instruction code, I have to, again, so you're checking the x/mem destination field, and you're supposed to check the ID/EX, meaning this instruction's source 1 or source 2 field. But none of the fields are actually available in this data path. So I have to slightly modify. Okay, I have to slightly modify the data path such that I'll pass my RS1 and RS2 to this ID/EX register also. Okay, why am I doing that? Because I need to know if my destination register is matching with the source field of the next instruction. Okay, to be able to know that, I need to store my RS1 and RS2 field in the ID/EX register also. So that is why I'll be sending my RS1 field as well as RS2 field to this pipeline register. Then I can make a comparison. Okay, then I can make a comparison and check whether the destination field here is equal to source field here. Okay, I'll check for both sources and see that it is matching. So this destination is matching with this destination. Only then I'll send this value instead of this value. Okay, in other cases, I'll not send. Only if your destination register in the ex/mem pipeline register is matching with the source of the instruction that is there in the id/ex register. Okay, if those two match, only then I have to forward. So this is the case for X hazard. Okay, this is the case for X hazard forwarding. Now again, we talked about mem hazard. So let's say if I forward the correct value, so if I forward the correct value 3 and 0 will not be read, instead 3 will be taken. So what will be computed as sum? What will be the sum? Like S0 and S1 if it does, what will come at the output of ALU? What will come at the output value? 4 will come, which is the expected value. So instead of 1, which was wrong, now 4 will come and 4 will get loaded, which is the correct value. By the time that 3 has moved to the next stage, the data that you had computed has moved to the next stage because your instruction also has moved to the next stage, which is mem/write back. And in this condition also your S0, which is still having 0, so that is being read. Now from where should I forward the value and how do I check the condition? So now 0 should not be sent, right? What should be sent for S0? What should be sent? Which value should be sent for S0? 3. Now where is that 3? That is important. Okay, where is that 3? In which pipeline register it is? It is available now. It is available in mem/writeback register. Okay, this is the 3 that is available. And this is the destination register that I'm supposed to write this value into. And the same is being is used as source in the third instruction. So in this case, how does the forwarding work? So here, when I say forwarding, I'll be forwarding from output of this stage or from this pipeline register. I'll be sending the data to the input of ALU. So instead of 0, I should be sending this value. Okay, so I should be sending this 3 instead of sending 0. Okay, so that is how the mem forwarding works. So the earlier condition, I'll check the destination register here with the source register here. That is for X hazard. Okay, so similarly for mem hazard, what is the condition that I'll check? Can you tell me the condition? Meaning, when should I forward from the mem/writeback register to the input of ALU? So you have to identify the condition for that. So what is the condition for that? What is the condition for that? Which destination you have to check and which source you have to check? So you have to basically check for the destination which is available here in mem/writeback, and you have to check if this is equal to the source register which is available here. Okay. So in that case, I have to actually forward this 3 to the input of ALU and then compute. Okay. And then if you send 3 here, the computed value for after the execution of this, after it goes to the ALU, will be equal to 5, which is supposed to be written into S4, and this is supposed to be written into S3, and so on. Okay. So this is how the forwarding is implemented in the case of pipeline register, and this is how the pipelining actually works. Okay, with the help of registers. So the instruction will move through the different stages and so on. Okay. I think I'll stop at this point. Okay, so the other things we'll discuss maybe after your midterms. Okay, so till this point, you have for your midterm exam. Okay, so try to visualize. I mainly showed this lecture to help you with the visualization of pipeline, how exactly the forwarding works, how exactly instructions move through different stages. Okay, to help you understand, I touched upon this. Okay, so with this, I hope you have understood how pipelining actually works. Okay, but more details of this pipelining, again, we'll discuss them after your exam. Okay, so if you have any doubts related to any of the topics that I discussed, please feel free to ask them. Okay, so just to give you an idea, Okay, anyway, I'll upload the update the syllabus and the CMS. Okay, you can just have a look at that. Okay, so it will be till this. Okay, till lecture 18, you will have for the midterm exam. Okay. Any doubts? Any clarifications you require? So I'll upload these slides. Please go through them once again and try to get a feel of how the pipelining actually happens. Okay, at least the visualization of pipelining. Okay, which will help you to understand the concepts in a much better way. Okay, so if there are no doubts, then I'll be ending the session now. Thank you.